Okay, hello everyone. Thank you for joining us today. My name is Aisha and I'm one of your Solid State Circuit Society staff members. The topic of today's webinar is Democratizing IC Design, the IEEE SSCS PICO program, presented by Boris Murmann. Today's webinar will be a little over an hour and we will hold a Q&A session in the middle of the webinar and after the webinar. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar, and I will put the link in the chat box with instructions on how to obtain the certificate. The webinar and video and slides will be posted on the SSCS Resource Center after the webinar. Please use the Q&A section on your dashboard to ask any questions. I now invite SSCS Webinar Committee member Alvin Loke to introduce our speaker and give a few welcoming remarks.
Hi, good morning, good afternoon, good evening, everyone. Happy New Year. We're off to a fantastic, hopefully a good new year. We are absolutely honored today to have a very special guest today, Professor Boris Murmann from Stanford University, who frankly really doesn't need any introduction here. Anyways, just a few words about Professor Murmann. He's a professor at Stanford University in the analog mixed signal and also AIML area. Today he's going to be covering a topic that has really taken the industry by storm, academia by storm, and this is the topic of open source hardware development. Anyways, without any further words, Professor Murmann, thanks again for volunteering your precious time to educate us in this domain, and look forward to your presentation. Thank you.
Yes, thank you so much, Alvin, for your kind introduction, and I'm extremely happy to see so many people connected and showing interest in this topic. So today I essentially want to report back on activities going on within the IEEE SSCS and beyond to make IC design more accessible, more collaborative, and as a result, also a lot more fun, hopefully. So I want to show you quickly the outline of this presentation. So as Aisha mentioned earlier, there's basically two parts, and in the middle there will be a Q&A session so that we can make this a little more interactive. I first want to kind of give you a lay of the land on what's going on in general. Why am I even talking about this? What's the motivation? And then give you a quick download on the emerging open source IC design ecosystem and its associated movement. Then in the second part, I want to talk more specifically about what we are doing within the IEEE SSCS. And we have a program we call PICO, Program for Integrated Circuits Outreach. It has several subcomponents. I will talk about all of them, and these will evolve and hopefully get some of you involved down the road, because I'm also looking for more people to participate in these efforts. So it'll be fun to see what comes out of this talk, maybe people stepping forward at the end and say, hey, I also want to be part of this and do something. That would be a dream outcome for me of this presentation. So let's see what I want to say about motivation. So all of you are seeing these headlines every day in the news. There's a talent shortage in the general semiconductor space, not just in circuit design, also when it comes to device technology, people who would work in the foundry, develop the next transistor and so on. And so the general perception is there is a big gap. And when you read into these articles, they always tend to kind of convey the assumption that it's because this stuff is just not cool anymore. You just have to read deep enough into it. It seems like young people are looking for cooler things to do out there. This article spells it out more clearly. It says, why screw around writing Verilog when you can earn tons more money with Python, Java, or Go? And this is really the sentiment on the street, right? Why bother with this chip design thing when there's so much other stuff out there? And I strongly resonate with this, and I don't think it's because IC design is uncool. I think it's still one of the coolest things on earth. But in the meantime, since the days I started, there are so many other things that have picked up and evolved that people can do that are equally fun or maybe a little bit more fun. So here you see in these pictures all these things that young folks can engage in, and I'm talking about the tech-savvy crowd. You can do robotics, you can do PCB design, these little programming projects with Raspberry Pis and other platforms. Around this, you have hackathons. You can do AR, VR with existing hardware experiments. You can do machine learning. Here's just a very concrete example, and maybe some of you even participate in this. You go to ICCAD. There's a TinyML design contest. You get a small board. And within a few hours, you actually have your own machine learning system with a camera up and running, and you can talk to your friends about it and use it at home. This is all incredibly fun. And what's interesting about it is that all of this, in one way or another, is actually enabled by the integrated circuits that we have developed in the last few decades. It's just building on top of this. But the one thing I want to point out, and that is really where we're going with this whole motivation, is that a lot of these things that you see on this slide, they're incredibly open and interactive and collaborative. So we who have enabled this whole ecosystem actually do not live in the same world. IC design is not nearly as collaborative, and as a result, perhaps not nearly as fun. So I want to sketch this out a little bit on my next slide. So this is, you in school maybe, as an undergraduate or graduate researcher. This is really where most people learn IC design. And so your ecosystem, and I put it here in quotes because I'm not sure it's really an ecosystem, kind of consists of a few different pieces. So first, if you're in a good place that is well connected and you have a good professor and so on, you may be able to get a real PDK. I call this a manufactural PDK from some foundry under some NDA. And so this NDA basically makes confidential information tunnel through a wall that's otherwise pretty thick. Oftentimes we only get these PDKs and not much support and so on. So it's definitely not extremely ideal. We can't just live on these PDKs. We also need tools. And so these vendors of proprietary EDA tools, they give us kindly access to this, maybe for a few dollars, not much. And then they give us pretty complex agreements surrounding this. For example, we cannot modify the software. Some of the file formats are proprietary, and so on. So it's actually quite limited. And the support also turns out to be quite limited. And for a good reason, these companies, they make money with paying customers in industry. Why should they bother so much with university? Then there's another side to this, and while there's maybe a stone wall here and there's a fence here in terms of getting things through, there's kind of this steel wall on the side of IP. I don't think in my whole career at the university I have managed to get actual useful IP tunnel through this double, triple enforced steel wall. IP is business, it's expensive, it costs millions of dollars. When you're learning IC design or when you're at the university, you just don't get it. You're lucky when you get pad cells and standard cells, and that's probably it. So that's why I put ecosystem in quotes. And it also has another ingredient that you kind of see later in the talk that I think is actually important, but we're kind of neglecting it. There's also people in academia working on the tools. So I call that here your EDA friend who's also hacking along. These people actually often are forced to work with toy PDKs. Why? Because the manufactured PDKs agreement states that unless you tape out with us and actually measure your silicon, you can't use this PDK, you can't really do EDA experiments and then publish all these numbers that reveal how good or bad our technology is and so on. So these EDA people, they have grandiose ideas. They work on the latest machine learning stuff. They want to build a silicon compiler and so on. But the problem is you really can't absorb what these guys do as an IC designer. You can't talk to them. So there's really no path to giving them something or even telling them what you need or sharing your files, because one part is under NDA, the other part can't be modified. And so really, as the circuit designer, your dream is to make this 8-page paper or something that goes into the Red Rag or some other venue. And unfortunately, your EDA friends' stuff, which is very cool, which should actually be incorporated in your work, really ends up in the recycle bin and maybe just circles around in research. And these folks are pretty much on their own, and they have a very hard time to connect to the actual people doing silicon research. So I think now you see why, quote unquote, I call this sort of a pseudo ecosystem. There is really not much interaction, not much sharing. And honestly, this really takes out the fun. And the situation is very different in these other areas that I outlined earlier. So thankfully, and this is what I'm talking about here in this presentation, is there was a very big bang event in 2020 driven by Tim Ansel at Google. You see here in his LinkedIn profile, he's actually a software engineer, and he's done things with FPGAs and board level things. And I guess at some point he and his colleagues asked the questions, why is it so hard to make chips and get access to these things and work together and so on? Can't we change that? Can we change it if we invest a little bit of money in it and work with a foundry to convince them to maybe open source their PDK? And so over some span of time, I don't know how long this took, and some funding, they convinced Skywater to open source their 130 nanometer CMOS PDK. And this is really a big first. So it's not that this is another random toy PDK. This is a real PDK that makes products, underlies products. So when you design something in this technology, you can be sure that it's real and it can be manufactured. Google is continuing these discussions with other foundries, and so you can expect that more of these PDKs will be released. The latest one is from Global Foundries, 180 nanometer MCU flavor kit. And you see that all these things are available on GitHub, where you can clone the files and work with them and do whatever you want. So the licensing, open source still has a license underlying, and here it's the Apache 2.0, which is very permissive. You can essentially do almost anything with this, including making money and so on, as long as you cite the source on where you got these files from. So this is all extremely open. So I know a lot of industry people now say, yeah, but you don't have 3 nanometers and so on. And yeah, but wait, right? So 90 is already coming on the Skywater side. There's already a preliminary. And in terms of a long-term roadmap, really what Tim envisions is to have a whole hierarchy of technologies, and he's really involved in talking to all the players, where if we want to get people in early on into chip design, you actually don't need 3 nanometers. In fact, this 180 is probably the perfect technology for this. You can maybe allocate a small piece of silicon to a student early, maybe high school is the right point. And they pay maybe $20, $50 to get a small chip fabricated and measured if it's somehow sponsored or shared runs and so on. I'll get back to this a little bit later. So this entry point is actually very important for getting people interested in these technologies we already have today are good enough for this. So they're now available. Meanwhile, there is a push to extend this, and I personally don't see why there wouldn't be a 55 nanometer process available sometime soon if people pay for it to get it open sourced and to push hard enough, because honestly, this is not secret sauce anymore. If you just wait long enough, something like 55, 28 is very vanilla. I just want to remind people that, when I did my PhD, 180 it seemed like it's impossible that I could never access this. It was such a fancy technology. It was crazily guarded. And now, yeah, it's a little bit like doing PCBs, 180 nanometers. So the time will come when a lot of these really fancy technologies are also available to everybody through open source. We just have to be patient and recognize that this is not a 2-year project. This is a decade-long effort to kind of push this envelope and meanwhile grow the ecosystem from the bottom. So to those who are new to open source, just a few remarks, because it often gets confused with just something that's free. For example, many of you use LT-Spice, and that's a free simulation tool, but it's not open source because they don't provide the code to us, and I cannot modify the code and make it better. So it's not transparent, and there's no open exchange. So open source really says you share something, you make it completely open so that people can use it, change it, collaborate on derivatives of it. There's transparency on what it looks like, and the community, through its meritocracy, decides in the end what wins and what gets used. And so the benefits that have been seen in the software community now for about 2 decades is that you can gain productivity. You have a better way of managing complexity. I'll get back to this a little bit later, right? I mean, just in a nutshell, if you want to build a new e-commerce platform on the internet, you don't hire a bunch of C programmers to start writing low-level stuff. No, you build on huge open source packages that are already available, and you pay your developers to use these modules and customize them for your purpose. We don't have the equivalent of this in the semiconductor industry. The other benefit is there's constant community review. Everyone can look at the code, find bugs, improve them, issue pull requests and so on GitHub. And so there's steady improvement, and that makes reuse more attractive because you know what you download is actually vetted by a lot of people, at least over time. And then lastly, obviously, this promotes education and tinkering when everything is open and there's no NDAs to worry about. Lastly, open source does not necessarily imply free, because you can make money with open source. Just consider Red Hat, right? Big corporations run on Red Hat Linux. They don't download the software per se is free, but the support is not. So they pay Red Hat to make sure everything's running smoothly and gets updated, and there's quality control. But the code is actually still open source. The same is true for Ruby on Rails, which is one of these e-commerce platforms. You hire developers to customize it for your needs. So the terminology, and this is very important when people talk about it, is that there's a proprietary world and there's an open source world. And it's not commercial versus open source, because open source can be commercial as well. So when people say commercial tools, they really mean proprietary tools. You can have open source tools that you still make money with. And in fact, there are startups doing this, and I get to that a little bit later. So I want to also point out that open source is actually in our DNA. So I'm not old enough to have been around for the release of SPICE, but Don Peterson was a very smart guy, and he recognized in the 70s and late 60s that putting his SPICE code in the open domain, the term open source didn't exist back then, by the way, but putting his code in the open domain will only mean good things for the community and for everyone else. And you know how many SPICE derivatives there are now, and how good this tool has become, and how important it was for the community to have this. Imagine SPICE being proprietary from day one. We would definitely not be where we are today. Similar things can be said about Magic. It's maybe not quite as impactful, but it was extremely important for people to get into IC design and support this. So this world basically has lived on. Open source tools have continued to see developments. Magic is still actively maintained, and so is SPICE. There's now NG-SPICE is a very popular open source derivative of it. And there's also high performance versions, Zeiss from Zandia, that is in the open domain. There's a good schematic capture tool by Stefan Schippers that has become very popular. And recently, this is also sort of on the big bang front of things, DARPA invested a lot of funding in open source developments, and that led to very sophisticated flows like OpenRoad, which is a completely open digital place and route and synthesis flow, including timing analysis and so on. So you can design big digital chips with this as well. So this is constantly evolving, and this is by no means the whole list. So many academics are working on this, and there is more and more funding on the table for these kinds of developments. So these tools, if you want to install them by themselves, it can often be a little bit tricky, and this is why volunteers sometimes step up, like Harald Brettel, and they do something for the community, like build a Docker container. If you're not familiar with this, this is a software that basically runs a virtual environment on any machine. It can be your Mac, your Windows PC, your Linux box. You install this container, and then in one shot, you have all the tools that are contained in it. And this is the list of what he covers. I don't want you to read through this. That just basically has all the popular tools, and with this you can basically design chips. And so this is just as a hint, if you guys want to get into this and try something, you can install this container relatively quickly and get going. In terms of making things easier, Google is also investing some efforts on the software side, especially when it comes to installing tools, which can always be tricky because of conflicting dependencies and so on. So Johan from Google spends a lot of his time to develop packaging solutions in Conda to make the installations easier. I'll show you a little bit more on this later. The other cool thing that I will get into later is the possibility of running computational documents, essentially Jupyter notebooks that are written in Python, where you can document your design process, your design ideas. These are all things that have not been around until this whole open source ecosystem popped up. Now then, lastly, at the highest level of abstraction, a lot of people nowadays make use of cloud computing resources, and especially at universities, you tend to have these available. Google is giving out free credits and so on. But with proprietary IC design software and PDKs, you often can't even go there because you're not allowed to upload your stuff on a Google server and then do some experiments and optimizations. But this is possible with open source. One, because everything is open, and two, because you have essentially an infinite number of licenses also. So you can parallelize everything to an extent that you just cannot do anywhere else. So this is all sort of very interesting ingredients that are evolving only because of this new movement. Just to give you a feel for this, so here's an example from the Google guys showing how their RAD lab, which is basically this cloud workspace, can be used to do some design exploration. This is some optimization of a RISC-V processor, different parameterization, and they're looking at die area versus power. And then here you see the layouts as it evolves in real time. And so these cloud resources are incredibly useful for this. And this is something, again, this is very difficult to do without having an open source platform and infinite licenses and so on. So tools are great, and they're moving along. And in principle, you could push these tools with toy PDKs. But at the end of the day, no one will care unless you actually tape something out and you have shuttle runs. And so this is why Google decided to actually invest money also into the shuttle runs. And so here you see a snapshot of the first shuttle run that almost happened immediately after this first PDK was released. And 45 people designed chips relatively quickly, put them on these runs. 60% of them were first-time designers, and I guess most of them did something digital. See here, these big digital chips. There's also some analog stuff in here. Some people who just dumped a little sub-chip in here that they bonded by themselves. I mean, there's a lot of creativity here that's going on. So this has really taken off since then. And at the bottom here, you see it started humbly. You know, they made a few test chips, then there was MPW1. And here you see the increments. So every quarter, there's a good 50, 70, 90, 100 more tape outs. So in total, there have been now almost 500 tape outs. I guess more than 500 if you count MPW8. That's happening right now. Here also, kind of the regional aspect, MPW5 as an example. You see a lot of countries being involved in this. India is playing a very big role. Of course, the US is, but surprisingly, there's also Turkey and smaller countries, you know, Armenia, Slovenia, South America is also in it, Brazil, other countries. It's not all broken out here, but I think you get the picture. This is really a global thing. This is not isolated in the US. What makes it relatively easy to scale this was basically the move by eFabless, which was contracted by Google to kind of organize these tape outs and kind of be the Moses of open source design, is that they have made a harness SoC, as they call it, where you put your design into this white space, and around it you have pre-allocated pads. And at the bottom, you have a little service processor and a logic analyzer and things like this. So it actually turns out if you don't do something fancy, within a few hours, you could actually potentially tape out a simple digital chip. Of course, it takes longer to do something analog, but in principle, you know, the idea was really to accelerate this by having a template to start with. And again, something like this is just very difficult to do in the proprietary world. So let me now review, you know, what are the benefits of all these things to the different stakeholders and abstraction levels. Of course, the industry is extremely important, but feeding into it is a big research ecosystem, and then there's an education ecosystem below it. And we're trying to get more people into this on the education side. We want to make ICs cool again. And I would claim that in the past, a lot of the people who went into this path, at least in my generation, were physics-minded people. They were interested in transistors, and then they learned about VLSI and so on, but they kind of came more from the bottom side. I think the new opportunity that we're seeing here is actually to bring in a lot more of the software-minded talent pool. And it turns out that this one is about 10 times bigger. You can look at many statistics, and I think this is quite common sense, that the people who program hardware, that's a community that's about 10 times bigger than the community that actually builds that hardware. And it's quite natural. And in fact, this is the success story of VLSI. This is not a loss or some kind of failure on the hardware side. This is actually a big success. And we should now leverage this success and get these people in and let them help us develop tools and make it easy for them to spin chips. So what that means on the education side, right? The open source brings free tools, open collaboration. Try to run a class with proprietary PDKs. It's very difficult. Students don't sign NDAs. It's very hard to guard the information. So there's a little bit of a new movement in education that builds on open source. On the research side, I showed you the EDA friend earlier. Advanced tool development is thriving now with this new open source ecosystem. And then on the industry side, well, as you would imagine, there is probably going to take the most time for any change. But, you know, if we look at this as a 10, 20-year development, we'll see what happens and what can happen to shared IP and maybe startups and standardization on this front. So I want to highlight some of these with a few more detailed slides here. So on the education side, many universities are now starting these tape-out courses. Here's the one at Stanford run by Professor Priyanka Raina. And she's using, at least on the analog side, a fully open source flow that starts with Scheme, Xscheme, and GSpice, Magic, NetGen, and so on. And this has been extremely popular with our students. Basically, within a quarter, they learn the tools, and then another quarter later, they tape out their own chip. So in 6 months, they have a complete IC design experience. Here you see Weston's PMIC. He made an open power management chip. You can actually download it on GitHub. Some people have done it, and they're building new designs on it. Here you see his first measurements, and this is just really exciting to see kind of what comes out of this and the joy that the students have here. Then comes, you know, this Mehdi. This is kind of my EDA friend, I guess. He's also a circuit designer, but Mehdi at the University of Michigan with other professors, they're working on some very cool tools to kind of achieve better automation in design. So the traditional analog flow is very manual, and they're looking into automatically generating layouts and kind of developing new flows around this. And this is now also very much driven by developments in the open source space. And so there's an open version of their tool, OpenFASoC, that you guys can check out. This is just one example. There are dozens of these projects that are quite nice, and they work on machine learning techniques and so on. This is very exciting. And really, what needs to happen is that these things need to be used to tape out chips to get the feedback, and the community needs to look at it, and the community needs to improve it. And this is why open source is needed. It's extremely critical in this space. When I look back in the last 20 years, kind of working with people who did EDA work at universities, oftentimes what sadly happens is that they are the only ones using their own tool. And I think open source can really change this, that these tools become much more widely used and improved by the community. So there are startup companies. eFabless is one of them. I already talked about that. They're basically managing all these Google tape outs right now. They also have a chip ignite program, they call it, where you can also pay for these tape outs and basically get a guaranteed slot. And they're basically marketing as something that can accelerate your design. If you don't have too many in-house designers and you just have a piece of Verilog code, maybe their flow actually can get you a chip out pretty quickly, maybe for an IoT sensor or something like this. So this is an interesting idea. Chip flow also goes in this direction. They're helping product companies to make their own chips, custom chips, right, without hiring an IC design team, and they're doing that with open tools. Silicon Compiler, that's also a new company. It's a very ambitious project, I mean, as the name may suggest, but they're looking into this. They have some ideas on with object-oriented APIs, and their motto is make the complex possible while keeping the simple simple. And so they want to have this push button flow for ICs. You know, these things are long shots, but someone ought to be working on it. And again, this new ecosystem is a very good place for doing that. Now, lastly, and I think this is mostly where more of the inertia is, and that will take a very long time. When you look at kind of the bread and butter industry out there, you know, minus startup companies, they actually have these very deep silos, right? They also start with IP and PDKs. And then they develop almost everything bottom up. Whether it leads to differentiation or not, they kind of have to do this. They all make their own bandgap. They all make their own PLL. And the PLL and bandgap of company A is no better than that of company B typically, but they all put in the same labor. A lot of labor gets duplicated here. And the developments are becoming more and more complex, and it becomes less and less manageable to design chips in a shorter amount of time. The software industry is managing this complexity by having a shared stack. So they all built on Linux, which is open source, and then comes these example packages, right, that everybody builds on. This is not differentiation for your business. This is just something that allows you to move faster, and everyone shares it, invests in it. And then you build your billion-dollar company on top of this, and you build it in a couple of months and not 9 months and so on. That's how long it takes to build a chip. Obviously, the problems are also very different in terms of the requirements, but it's definitely fair to say, this was pointed out by Andreas who was at DARPA, that the software side is better at managing complexity and avoiding duplication and deep silos. So we will see if this will, if a sliver of this ever goes on this side, and I know the industry folks will now say on this talk, this will never happen because of reason ABC. But you know, the time will tell, and one should never say never. So this gets me to the point where we can do the first Q&A. And I guess Alvin may be moderating this. I don't know if I can.
Yes. Yeah. Can you hear me,
Yeah.
Boris? Okay, great.
Yes.
Yeah, I say thanks so much for this excellent overview of the landscape and so forth for open source. Just a reminder for folks, if you have questions, please type them into the Q&A box. So I did want to actually make a comment that personally, I think it's a good thing that people who are starting, students who are starting, get started in much older nodes, because working in the new nodes isn't exactly as wonderful as it may seem. You spend way more time thinking about second order things like obnoxious DRC rules, and less time thinking about actually the design itself. And although this is something we have to do and learn how to figure out to be DRC clean, you know, just taping out in advanced nodes, as you know, is largely is a lot of perspiration. So the first question that showed up, do students in the class, this is slide 17, know circuit design in the first place? For instance, understand power management, op-amp design, and so forth?
Yeah, the good news is they don't necessarily need to, because you can basically flip this around. Your first chip can be digital, right? And so you actually may do your first tape out on a little small accelerator or a RISC-V processor, and there you learn while you do that. And again, the tape out is cheap, right? There's not this barrier anymore. You have one tape out in the next 3 years. No, you can tape out something every quarter. So you start with a little digital project that makes you comfortable with the tools. You learn the CMOS cross section. You don't need to know BSIM models or something at this point. You just get your hands dirty. And then later, if you want to do analog, you learn that. And in parallel with your first taping out digital stuff, you may take some analog classes and then you learn that. So this can certainly, again, because this is all much more agile, we should get rid of this idea that you first have to know everything about electrons, and then you need to know a NAND gate and delay, and then 3 years later you maybe get to tape out something. No, that doesn't have to be like this. The idea is actually the opposite. So a lot of the people who tape out now, they're programmers. They actually don't really know how the transistors work, and they don't need to, but they can find out later if they want on demand.
Yes, I think there's been circles of us who have kids who play with Redstone, I guess, which is a part of Minecraft, not realizing that they're actually building state machines as they're playing
Yeah.
a computer game.
Yeah.
Some other questions coming in. Who supports the tool issues during the design phase? Seems like the most common problem.
Yeah, this is a problem. This is also a problem in the software community. I mean, I'm by no means an expert on this, right? But it's basically maintained by the community. So when you have a problem with a tool, you basically raise an issue on GitHub, right? GitHub, right? There's a button, you go to the whatever where it's hosted, and you raise an issue and say, hey, this is not working. And a lot of times the developers will actually almost immediately fix this because they want this to happen. Or maybe someone else fixes it. In fact, you can fix it too if you want to. You can make a change to their code and then issue a pull request. I mean, this is in general how open source works, that the whole community maintains the code. But in reality, there's typically a few individuals who do this. And so I have actually seen it. There's Tim Edwards is one of these guys. He actually maintains Magic. I see a post somewhere on Slack saying, Tim, it would be really nice to have a new button here. And then he makes it, and 3 days later you have it. So there's some really interesting things going on. But generally, yeah, this is a problem. And I think as the community grows, right now it's about 5,000 people invested in this. As the community grows, I think this is becoming less and less of an issue.
Got it. So there are lots of questions related to PICO. I'm going to defer to those until you actually have some time to describe the PICO program. Yeah. But one question that's certainly on people's minds is, okay, well, how do we incentivize industry companies who are in the business of essentially making money off their IPs to contribute to an open source ecosystem?
Yeah, so I think the IP and the open source ecosystem will eventually not come from companies necessarily. I mean, maybe from some of the startups, but the community will create that. And we're basically en route to this, right? So you can now find some band gaps, and people are building USB interfaces and simple things. I mean, I'm not ready to say that it's actual IP yet. It's still kind of in the test phase. Look, I mean, this is on a two-year-old effort here. But I think over time, you will actually see an IP ecosystem develop that is driven by the open source community itself, by all these tape-out classes, right? Imagine if every university has a tape-out class, and they all contribute a different piece of IP that gets improved over time and brought into a shape where it's actually tested and trusted. That's extremely powerful. So I don't think the companies have to solve that IP problem, at least not for the university side. Although there are some startups that are looking into that as well. But honestly, I think I'm not qualified to make stronger predictions than that.
I see. Which I guess gets to another follow-on question that several have asked is how can working professionals participate in this if we're not contributing IP?
Yeah, maybe I'll get to that a little bit later, because
Okay.
that's also the idea of PICO, right? To get people together and contribute. And I will actually have a specific request for people to help. So yeah, I will get to that.
Yes. Yes. Okay. Well, in the interest of time, let's continue with the rest of your presentation, or the other
Excellent.
half of your presentation, and we'll take more
Yeah, and
questions
thanks
later.
for your questions, everybody, which are very good. And I will be happy after this presentation to get together with people and talk some more if you want to. So, so meanwhile at the SSCS, right? So what you just saw is the general community activity, right? This happens whether there's an IEEE or not. We're not really the founders of any of this, but we want to play within this. And so luckily, around 2020, just around then, the Solid State Circuit Society to form a new committee that looks a little bit into future directions, what's going to happen in ICs in the future. And very quickly, this committee picked up the trend of open source and identified it as something important. We held a workshop. We identified some speakers from the open source community. We had them present to us. And then very quickly decided, this is something that we need to get involved in, because we are one of the key forces in the IEEE to own this whole idea of IC design and getting people into the field and so on. It's in our interest. So that's when we decided to establish this project that we call PICO. And again, I will outline in detail what it's about. And then in addition, just this last year, we created a dedicated technical committee on the open source ecosystem, TCOSE, that I'm chairing now. So this is really a message sent by the society to say, we're very interested in this, and we're going to have some brains within our society, think how we can help, and also how we can provide value to our members, right? So this talk is one of these, right? Getting briefed by the SSCS on what's going on in the open source ecosystem. That's certainly something that our members want. And so this is a quick snapshot of who's on my committee. If anyone is interested in joining and has bandwidth, please let me know. It's essentially a group of people who are already enthusiastic about these things. So, Harald, I mentioned, he made this Docker container. Priyanka is teaching a tape-out class. Mehdi is doing all this fun EDA work and so on. Mariana, she's working on BAG and programmatic design flow. So all of these kind of have a foot in these things and are very excited. They all invest a significant amount of time. So being on this committee is not a participation trophy. We actually expect people to do actual work, invest a good number of hours per month to do something that helps us get ahead. So our charter is to run the PICO program. We develop a vision for publication. This is the thing that I haven't gotten into here yet, because a lot of this silicon will want to be published. How do we do this? And we're thinking very hard about in the IEEE on how we get this integrated into our conferences. I'm not getting into that much today. For now, it's mainly workshops. There is, though, if you come to ISCAS in May, there's a first session on open source IC design results. You will see at ISCAS this year. So it's slowly picking up. We want to collaborate with other players. Again, we're not owning this. This is way too big to be owned by an IEEE society. It goes way beyond that. And we just want to continue into this pool of making examples, curating best practices, and so on. And so one of the things we did is actually we made a website where you can go and kind of start reading a little bit on what are some of the key pointers to links, how do you get started, where you download things, and so on. So this may be an interesting resource for anyone who's completely new to this. Start with this page, read it, and follow a few links, and then off you go. This is kind of your best entry point. So now here's what we do. So PICO, think about it as a program that will evolve over time. It will have new program components over time, and new people will join, new ideas will evolve, and so on. And so for now, I want to report what we have going on right now. First, a travel grant program, then we have the open source chipathon. And then later, I want to talk a little bit about scaling up and actually reaching more people than we are reaching now, potentially. So not necessarily in chronological order, but one of the things we're doing is the Coded Chip Travel Grant Award program. This, by the way, is open to anybody. You don't have to be a student. You can also be a professional. The idea is to code a chip in a Jupyter notebook, and I'll show you in great detail what we mean by this, and then show your results at a conference in a small session. And so this year we did this for the ISSCC. We had a deadline last November. People submitted their designs, and then we picked 7 of them as winners. I'll show that a little bit later. And so the society received a generous donation by the CHIPS Alliance, which is an industry alliance that coordinates open source activities between several companies. They made a donation, and we used that essentially to pay for the travel and all the other conference costs for these attendees. Basically to bring open source people to these venues and get them connected and show their work. So what is this? What is the main idea behind this? What do we mean, coded chip and so on? So one of the main motivations behind this is reproducible IC design. So even if you publish your design in the Red Rag and the Journal of Solid State Circuits, I still almost have no way of duplicating exactly what you did. I cannot, even though I see your circuits, maybe I see your architecture, maybe I can guess what some of your W over Ls are, maybe I can do something about it. I cannot duplicate it. So the way we report results and disseminate designs is just not optimal. And in more complex areas such as software, this is basically solved by releasing papers with code. There's literally a venue that's called Papers with Code, and also machine learning conferences and so on. Your paper comes with a piece of code so that everybody can duplicate your results. So for academics, this can be extremely important to show credibility on what you did. What are some of the design choices you made? Teach people how something should be done. This is now, because of open source, also possible in IC design, because everybody has access to the same licenses. There's no license barrier. I don't need the same Cadence license you had. We just both use the same open source licenses. If we're both designing in open source. So this can be organized actually very nicely, for example, in Jupyter Notebook. And here's one of these Hello World examples for digital. So Google put this together. This is a Jupyter Notebook that can combine text and program execution in one frame, in one document. So you install tools, you write a piece of Verilog code, and then you run this open lane flow, digital place and route, and then plop comes out a layout at the bottom of the document. So obviously, this is a simple example. You can imagine doing this for a more complicated chip. You can also imagine doing analog things. So let me show you here a Hello World example for analog. This is actually my own. You can go to my GitHub and clone this. So here I use Google Colab. Anybody can go to Colab with their Google login, and they you make a new Jupyter notebook. And then here I took some setup from Propy. You initialize a Conda environment so you can easily install the packages. Then I install ngSpice here in this document. And then I put in a little netlist. I'm a Spice guy, so I write a little Spice netlist here. Then I run ngSpice in this document. And then I get some data out, and now I can use all these Python packages like pandas. This is very nice for manipulating data, and you can kind of look at it as a table. You can also plot it with these functions in Python. So this is really cool, and I have actually started to work with these kinds of things for my classes as well. I prepare my homework solutions in these types of documents. Basically, everything is self-contained. Again, you can load whatever tool you want. Obviously, this is very trivial, so let's show a much more sophisticated example. This is actually from Mehdi's team from Michigan. So this is actually, they design an entire digital LDO in a Jupyter notebook. So you can start by basically describing a little bit what's going on. Here's some references and so on, and then you can have a description, very much like an intro to a journal paper, and then you show the overall schematic. This is what we're trying to do. And then in this tool, they initiate some of the tools. So they have various tools they use: Yosis, K-Layout, Magic, and G-Spice, and so on. They install all these tools. They have a predefined netlist here in this example, I guess, for the regulator. But anyway, I don't want to walk you through all the details. You kind of see the flow. You have a mix between text and documentation and actually runtime execution of tools. And at the end of it, a layout comes out. So this is an auto-generated layout for this LDO design. It pops up in the same Jupyter notebook. You just use some plot functions from Python. And then at the end, in the same flow, you can then also do post-layout simulations, for example. So if you share this notebook with anybody, they can run it and they can duplicate it, and then they can maybe change it to make a slightly different LDO and so on. And so this is extremely exciting, in my opinion, and this is a first in IC design. We have never reached this level of transparency, I would say. And while there's a long way to go, right, in making this pretty and kind of clear to everybody and maybe more sophisticated, less cryptic, I think it's a fantastic opportunity. We all go around at conferences saying, I don't believe what these guys measured. This probably doesn't work, and so on. Well, if everything was in a Jupyter notebook, you just could go run it and see if is that actually real or not. So we'll see how much this takes off. We want to stimulate these things, and this is why we have this contest. So here is the 7 winners that will present at the ISSCC. You see geographically is also very much distributed. We have China, Japan, Chile, USA, South Korea, Belgium here doing things. And you can go to GitHub and look at their notebooks. Some of them are very long. Some of them are maybe 100, 200 pages, but everything is there, and you can run it. So it's pretty cool. And again, like I said, this will get better and better. This, by the way, is open to anybody. We're not even requiring IEEE membership. We actually want to bring in people into our field, into our community. And so even if you're not a student, if you're a hobbyist, just sign up next time. So we will have future editions on this. Stay tuned for announcements. We're working on this. Nothing is determined yet, but the idea will be maybe to travel also to other conferences, via VLSI, CICC, and so on. And so this program is expected to expand, and I'm extremely excited about it. It's just a new dimension that we have never gone into. So now a much bigger thing has been the PICO open source chipathon. And here you see the ad on the event for 2022. We also did one in 2021, and we're basically building on the existing capability that eFabless enabled with this harness. And we basically told people, send us your proposal. What do you want to design? What is your design? And if it's reasonable, if it's fun, you'll be invited. And then we will help you get this design out within about 6 months or so, get it taped out, and we will pay for the tape out. So we're not using free tape outs here, but the society, Solid State Circuit Society, has actually paid for the silicon. It's quite affordable. It's not super expensive. So give you a feel, in 2021, we had 61 submissions. We selected 18 teams. 11 ended up taping out. 54 submissions in 2022. Fewer but higher quality, in my opinion, and then we selected 2022 as a result, and 14 of them taped out. And so you see, again, this is a global effort. We're very low on Asia. I want to figure out what to do to get more Asian folks involved in this, but obviously we have strong presence in South America, North America. There's some Europeans, there's Egypt, Afghanistan, India, and so on. And so here you see, we have weekly meetups. There's a kickoff in June, over 100 attendees on Zoom talking about open source, things they want to do, problems they have. The tool experts are actually in here also, or we invite them when needed, like Tim Edwards, who runs Magic. We invite him, and then people can talk to him. Look, this is what's wrong with your tool, and so on. It's a very fun and open exchange. So this is the kind of overall timeline. You know, we have a kickoff. We make people do a mock tape out early on so that they know what's involved actually in pressing the buttons. We help with design reviews. We help with layout review if needed, and then we tape out. And so, like I said, we meet weekly. There's not always 100 people there, but often 50 or so. There's a lot of side channel communication via Slack. There's a public Slack channel that you can sign up for and participate in all this. It's one of the most fun things I have ever done in my career, simply to see so many people and hear what they do. And you can actually talk about polyspacing in these Zoom meetings with strangers, something I have never done in my career. So here's an overview of what was taped out in 2021. You can kind of get a feel for this. Some of the teams, at least, they managed to combine multiple designs on one chip. And it ranges from relatively simple things like band gaps, simple temperature sensors, all the way to kind of neural network accelerators and things of that nature. And again, this was taped out via the paid ChipIgnite program, and everything's open source, so you could look at it. There's also articles that we continuously push out into the magazine. You can read more about what's going on here. This is what happened in 2022. I would say the designs became a lot more sophisticated. There was also more sharing. We have 14 teams who taped out. There's some massive collaborations here, like this DC-DC converter. There's a team from Chile, Argentina, and Uruguay working on a CubeSat, and they got together to build a DC-DC converter. This is really fun to see this, right? This is something that is not possible before open source, because even if I want to work with my friend at the University of Michigan, we cannot tape out together because it would require a three-way NDA, and the lawyers will not work for us to make a three-way NDA, right? So none of these things are needed here. Everyone can just work together, and we're having a blast. This is just a fun aside. You know, this is Jorge. He was on the Chile team that worked on the DC-DC converter. He's getting interviewed by Matt Venn, who's also very active in the open source space. He runs a YouTube channel. He's kind of the open source YouTuber, you know. He makes fun interviews. He has some news. He also runs a program called Zero to ASIC, where he teaches people who know absolutely zero about chips and semiconductors to tape out a chip in a month or so. Something simple, maybe a counter, a digital clock or something. Anyway, these things are picking up, and it starts to feel a lot more fun than it used to be. And this is just one of these examples. There's also something to be said about diversity. We're enabling a lot of people with these programs who would normally not be able to tape out, and you know, kind of bring them together and just make this a lot more inclusive than it used to be. It's IC design comes from the angle of an elite sport in the past, and it should really become a sport for everybody. And I think we're contributing to this. So here's an article. Meet the Chip Athletes, you know, who was participating. They write a little bit about why they're doing this, where they're from, and things like this. Kind of fun to do these things. I should also acknowledge here, you know, beyond the little committee that I'm running, there is a lot of volunteering going on. Every week, I tend to invite someone else from this roster who can talk about certain things. Like Eric, for example, came and he explained to people what LatchUp is. And so we have these sessions, we mentor students. And so if you're interested in doing any of this and participating, you can actually sign up. There's a link on the SSCS website. I periodically look there and then ask people to participate. And there's a lot of things you can do. You can become part of the meetups. You can help us evaluate proposals. You can do some presentations. We can sort of talk and see what you want to do. There's kind of an infinite demand for people to do stuff, as you can imagine. Please sign up if you want to spend at least 1 to 2 hours per week. Again, this is not a participation trophy thing where you can say you're a volunteer, but then you just watch. We want people to roll up their sleeves. Now, a little bit of outlook. I'm almost done here. We are close to launching the call for the 2023 Chipathon. And we decided to do something a little bit more different this time that's more community oriented. So one of the things that does not yet exist, but would be very nice to have in the ecosystem is analog wave generator and oscilloscope on chip macros. So imagine you want to design a simple basic analog circuit. And again, I'm not talking about industry grade 3 nanometer, 10 gigahertz, no. For people who design a common stage amplifier for the first time, and they want to measure it without having a lab at home, how would you do it? If we could somehow manage to squeeze a nice waveform generator and a scope on these chips here in this service area, anybody could instantiate this, design something, and then test it with just a PC. And so we want to see if we can bring teams together who can generate this type of IP, and we will obviously structure this in a way that's doable and get to a first tape out of such a system, such a subsystem. The good thing is once we have a first prototype, this can continually improve over time, right? This is the whole idea of open source. So this is what's coming. This needs more work, and we will hear about it maybe in a month, 1.5 months or so. We will announce this pretty soon. Now, the last thing I wanted to talk about is, and sort of the leadership of the SSCS, and others are asking me this, sort of nice what you guys do, but it seems like there's only a dozen people involved here and there. You have this few people traveling, few people taping out. How can we make this much bigger? So Matt is actually, the guy who also runs his education program and YouTube channel. He has sort of figured this out on the digital side. He runs something that is very cool for beginners. He calls it tiny tape out. He takes this 10 square millimeter, and then he cuts it into many tiles, hundreds, it depends on how big he makes it, but several hundred tiles. And in each tile, you can fit something like 1,000 logic gates. And then he has a sign up, and he has a very simple tool chain where literally within a few days, you can build your own little digital system up to 1,000 gates and get it taped out for something like $50 or something. And then you get it back on a little board and you put it in your USB. You wouldn't believe it, but a lot of people who do software, they're craving for these kinds of things. When you're coding and you want to do something in hardware, this is really, really fun. Now, this is limited digital. How do we do it for analog? And I think this is where I want to do something next, and I'm looking for people who may be able to help. Matt is actually very interested in working with us, but we need a lot more people to make this happening. And in fact, if you think about it, this thing we want to design for our Chipathon, it can actually be a starting point for this, where now, instead of having digital tiles, maybe we have analog tiles, maybe they can be a little bit bigger, but when you have instrumentation on chip that can be muxed around, then a lot of people could design simple analog circuits. And again, don't tell me that I can't do a 5 gigahertz LNA, that's why it's no good. That's not the point, okay? There are people who want to design very simple things, little amplifier stages that run at kilohertz. And for that, this is perfect for getting kind of a foot in the door. And that's, I think, how we get some of the masses into IC design and make this really popular. But this is future work, but very much in the spirit of what we want to accomplish with PICO. So this is time to summarize. I think you sensed it, at least on my side and many others, there is enormous excitement about having a more collaborative and open ecosystem for IC design, and open source is really the way to do it. It's definitely changing the way we teach. There's no question about this. It may have impact on the way we work. This is to be seen, and it may take decades to do that, but everything has to start simply, and that's where we are right now. The community is growing pretty fast. We're at about 5,000 people now, and I count that based on Slack channel membership. This is definitely growing, and just for reference, the entire IEEE Solid State Circuit Society is about 11,000 members. So this is already half the size of the IEEE SSCS, and it's going to be much bigger very soon. So this is something that you cannot neglect and that you should pay attention to. So PICO is kind of our foot in the door, or our contribution to this community. Why we want to engage with this community. We want to come up with fun things that benefit our members, get new members interested in the society, and at the same time provide volunteering and mentoring opportunities for members that we already have. There are plenty of people who are maybe retiring, but they want to stay involved. I think this is an ideal activity for anyone to get in who wants to still be active in retirement and so on. And so I really want to call everybody here to let's work together. Let's not be pessimistic about why this shouldn't work, but let's make it work. And let's see how we can add a totally new fun factor to IC design with all these new capabilities. So thanks for your attention, and I'm happy to do a few more Q&A depending on how much time we have. Thank you.
Professor Murmann, thanks again for this incredible presentation. Bunch of questions, and folks, if you have questions, please type them into the Q&A panel, and we'll do our best to get to them. So, questions related to PICO. How can we use PICO to target high school and middle school students?
Yeah, this is the billion-dollar question, I think. And the kinds of things I talked about at the end is basically going in this direction, right? If there's a path for taping out very simple structures with a few mouse clicks and doing that very efficiently with a few tens of dollars, this is also something that Tim Ansel is talking about, that Matt Venn is talking about. I mean, in digital, it can already be done, and Matt has shown this. I think what's missing is really the people who can really do this type of stuff, right? I mean, how do we get high school teachers to master this and to actually teach people how to use the tools? And so the tools have to become simpler. And Matt, please do have a look at his stuff, has shown us how to do it. He has a toolkit in a web browser that everybody can use to make a little digital circuit and get it taped out very quickly. That's the kind of stuff we need. And so we need to bring in teachers who love this and want to show it to their students and get them excited about it. And I think it's doable. It just needs more work.
And just a little bit of a shameless pitch. The chapters for solid state circuits are being encouraged to basically do more pre-college activities and engagement. And some chapters have already shown a lot of pre-college work and getting them more involved in evangelizing PICO would be a good thing. Is PICO open to working professionals?
Absolutely. It's open to everybody.
Yep.
Yes.
And another question related to open source is the meetings that are run for to share the means that you talk about, where you exchange poly spacing rules and so forth. Are these open to everyone?
Yes, absolutely. Yeah.
Okay. Okay, great. Okay, just I knew that, but I just wanted
you can go on the internet and look it up yourself right now.
Okay,
so yeah,
good.
That's the whole idea of an open source PDK. I mean, obviously, you will find, if you work at a well-oiled company and you see what kind of support you get from kind of a commercial vendor of proprietary PDK, you probably have better documentation and support. But these things are improving. It's actually looking quite good already.
Yeah. Okay, and a bit of a rhetorical question: is it possible to do analog design in a collab notebook?
Yes. So we already have some examples there. So when you go to that link I shared, I mean, we're going to post the slide, so you will have all the links. So there were a few people who did something analog-ish. It's, of course, a little bit harder, especially if you want to do the GDS generation at the end. Analog layout is typically manual, but there are some automation approaches. For the coded chip, I should say that it's actually not mandatory to produce a layout. So a good analog project could just be maybe some design study, maybe with some interesting optimization methodology, some code wrapped around some SPICE simulations or calculations, sizing exercises to look for some optimal topology. I mean, it could be something like this. Yeah.
Got it.
It's definitely possible in Jupyter, yeah.
Okay. Now, if fabs release their PDKs, EDA vendors should do the same with their tools. Otherwise, the ecosystem will not grow. What's your opinion?
Yeah, this is a good opinion. Go tell them. I'm not sure. I mean, maybe some of this may happen, and I get this question. Maybe I answer a little bit of a different question first, and that is, I forgot who asked me this. Maybe even you, Alvin. You know, do the commercial vendors hate this open source stuff? You know, if you sell these tools, do you hate this open source movement? No, it's actually the other way around. So the people who work on OpenRoad, for example, these are exactly the people you want to hire into your company. And these companies that make the high-end proprietary tools for nanometer design and so on, they love it that they can get people, you know, trained on a playground that is somewhat still real, right? There's a lot of real things there, even if it's 0.18, you learn all the basics, and then you can be hired. Now, without this open source training platform, if nobody works on these tools in the open domain, who are you going to hire? Right? You actually need this ecosystem. And so when we go to these open source meetups by the NSF and so on, all the big EDA vendors are there. And they say, keep going, keep pushing, keep doing this. We actually need this. So at some point, hopefully they will recognize that they should also make contributions to this then. And maybe we will see something happening. It's quite possible. But again, I'm not really at the right pay grade to say more than that. But I'm pretty hopeful because there's no competition. Just like there's proprietary software operating systems and open source systems, these two ecosystems, they live in parallel and they feed on each other, and it can be exactly the same in EDA.
Got it. So, I mean, I've been told before that 10,000 lawyers at the bottom of the ocean is a good start. I hope I'm not offending any lawyers here. I mean, what are some of the legal challenges that you've seen and you've been exposed to and had to deal with to get to where we are today?
Well, I mean, the whole point with open source is that there aren't supposed to be any legal challenges, right?
Yes.
I guess the legal challenges, they are on the side of the companies that are releasing the open source tools, right? Like if a Skywater releases their open source PDK, I think their lawyers will look at that and make some assessments on what the risk exposure is or whatever that entails. But I personally haven't talked to any lawyer about open source because I'm on the consumer side of open source, and then it's very clear there are these licenses, and typically everything runs under Apache in our space, which basically just says you can do almost anything with it if you just kind of state the source of it. I should point out that I mean, the open source ecosystem kind of benefits from having the software folks have already gone through this, right? So in software, it's very clear how to do open source and how to license it and so on. For example, this PowerPoint software that I'm using to project to you right now, it has hundreds of open source packages underneath. You think that Microsoft wrote all this? No, absolutely not. It's a bunch of open source stuff compiled together. And so, you know, this has been figured out. And so I think the legal angle, if you're a hobbyist or if you're at the university, there's really nothing to do for you.
That's good. So no concerns with patent trolls or anything like that?
I'm not aware of anything like that.
Okay. Like I say, you know, some of the things that I hear people claim from a legal perspective sometimes blows my mind, the creativity that comes out of there. Another question related to tape out. So are there future open MPWs planned? And if presumably yes, what type of cadence?
Yeah, so these free Google runs, they occur every quarter, and they will only step up. So you'd have to, you know, Google some material by Tim Ansel. He updates the community often about this. So we're just starting with Global Foundries now. So there'll be parallel paths. You can go to Skywater, you can do to Global Foundries. There will also be more tape outs in Skywater 90, that's also coming. So the volume is basically going up, and I think the cadence is roughly every quarter there's going to be some tape out or multiple tape out. So the opportunities will only go up. Yeah, and especially, I mean, if you have some money, if you have a few $1,000s, you can also pay, and that gives you maybe extra access. But in general, these older technologies are pretty cheap. I also know there's some fancy stuff coming. I think IHP is about to release an open source PDK and access to their technology. So if someone who wants to play with silicon germanium will also be able to do this in the open source framework.
Got it. Well, I think we're already 20 minutes past the hour. Any concluding remarks you'd like to share, Boris? I mean, clearly there's a lot of enthusiasm, energy here.
Yes. Yeah, I'm extremely excited, and you know, I grew up in this IC design world in its closed format, and I really feel a fresh breath of air going through the whole community now that we're building, and I really hope to get some of the sort of more traditional people involved to help us build this new ecosystem, so that we can learn from their wisdom and all this. But yeah, this is about as much fun as I've had in my career, and that's why I'm pushing very hard on it. And we all need to have a little bit patience, and we need to be optimistic about the future and not ponder so much about on why things can't be done right. But let's be very positive, and let's see what we can achieve with all this.
With that said, I'm really glad you're our fearless leader.
Yeah.
Yeah, with that said, you know, there are a bunch of questions related to, you know, how you can get involved, how you can participate. This is obviously a very, you know, a caring and very generous community. Yeah, I mean, Boris, you mentioned that there's plenty of there are websites you can just search to participate in
Absolutely.
your meetings
Yes.
and so forth. And a little bit of a shameless pitch on my side. You know, we love you know, our Solid State Circuit Society members, but we love even more active Solid State Circuit Society members. And so please don't hesitate to reach out to the society or your local chapter leadership in your local geography to see how we can help out. Okay. Well, with that said, thanks once again, Professor Murmann. I really appreciate this inspiration. Aisha, let me turn it back to you.
Thank you, Alvin. This concludes our webinar. For any more information on our upcoming webinars, please visit the SSCS website. Thank you, everybody.
Bye-bye.
Bye.
Thank you.